Okay, guys, so sorry for the delay, but we had some technical issues here. So basically, I think last time the problem we finished was I ended up having the impression that you got a little bit lost. Okay, so let me do like a quick review of one part of the material covered on that problem, but it's also some material that we covered probably about a month or 2 months ago. Okay, so a long time ago, probably about a month or more, we derived something that we call the Tds relations. Okay, but basically what it means is this, is that so far what we have derived, so let's say review here. Okay, so basically we have something which is the first principle of thermodynamics, which we wrote the equation Q minus work generally will be equal to, if we neglect kinetic and potential energy, this is generally equal to the change in internal energy. Okay, so in this equation here, let's just say that or we can rewrite this just for this case here, for this would be equal to this. Okay, but this is the first principle of thermodynamics. Then we derive something called the entropy. So entropy is like Newton's law. It's something that is not derived, it's something that is given to you. Okay, so what is the entropy? We say that the change in entropy, let's say ds, we also call it delta S, but we're probably going to use ds, was equal to what? Was equal to the change in heat divided by the temperature. Okay, so from here we can see that the change in temperature basically is equal to Tds, and that's where the name Tds relation comes. All right, so now what do? If we substitute this expression here, which is from the entropy, into the first principle of thermodynamics, what do we obtain? We obtain Tds minus the work will be equal, let's say, to the change in internal energy. So really this equation, if you think about it, is just the first principle of thermodynamics, where we have replaced the heat by the expression with function of the entropy. Okay, and this is what is generally known as the second principle of thermodynamics. Okay, but what happened is that under this form, generally is not used much. Is used under the form of Tds relation, because what were the limitations of the first principle of thermodynamics? Is that first, this equation assumed that everything is 100% efficient. Okay, if you want me, let's do like a review. This equation assumes that this is your system and this is your hot reservoir. This basically assumes that all the work, all the heat can be transformed into work, no? All the heat transfer can be transformed into power. That's really the first principle of thermodynamics. However, what do we know is that any system is always going to operate between two temperature reservoirs, no? One Q hot, one Q hot. So if you remember, we derived some expressions for the different efficiencies. Okay, so that was one of the limitations of this equation, but we overcame that one by writing the efficiency equations. The other limitation of this one is that we say that this equation, let's say if you limit this, you get Q equal to work, or Q equal to work over here, which means that you can transform other heat into work, but vice versa, you can transform other work into heat. And this equation, you can go back and forth indefinitely, no? However, what do we know is that not every process is reversible, or you can do it forever. I gave the example, which is not completely physically correct, but as an example is good. You can go from liquid water to ice water, and then you can go from ice to liquid water again, and you can restart again this process as many times as you want, okay? From the thermodynamics point of view, it's not really true what I'm saying, but the concept it is. But if you burn a piece of wood or log, you get ashes, but then you cannot get the wood again from the ashes, no? So that one is in one direction. So one is reversible, the one is not reversible. So in order to know if a process is reversible or not reversible, we define a new variable, a new quantity, which we call the entropy. And we say that if the change of entropy was equal to 0, that means that no energy is lost, and you can go again back and forth. But if the entropy is positive, means that you lost some of the energy during the process, okay? And the system becomes irreversible. All right, so anyway, so now we have here the first principle of thermodynamics, rewritten in function of the entropy. So this equation needs to be used in order to find what is the change of entropy, to know if the process or the cycle will be reversible or non-reversible. And this will be the Tds relations, okay? So what do we have over here? So in general, knowing that what is the expression for the work done by the pressure? Remember, we had integral of PDV, but since this is the partial, we eliminate the integration sign and we have PDV, okay? So if we substitute into that equation, what do we get? Tds minus PDV equal to du, okay? Or this will give us Tds equal to du plus PDV. Okay, so this is what would be known as the first Tds relation. Now, again, I'm doing a review. I'm going to give a lot of information. So if you remember, if we are dealing with U, internal energy, generally, what does that mean? With what type of system we will be dealing? Correct. So basically, you know, the U will be proportional to the CV, and we'll be dealing with a closed system. That basically will mean that is a fixed volume, or it might be one of those piston cylinder systems, no? Okay. So anyway, we have this expression. Okay, so next we use another quantity that was defined. What is the enthalpy? The enthalpy by definition was what? Internal energy plus PV. Let me rewrite it. So enthalpy is internal energy plus PV. Again, I did all this stuff in a previous lecture. Now, if I take the derivative of the enthalpy, what do you get? You get dH will be equal to what? du plus P dV plus V dP. Okay? You understand this part? All right, the derivative of uv is u prime v plus uv prime, no? In mathematics. Okay? That's exactly what I'm doing. Okay? So now, from this equation, I can rewrite du as being equal to what? dH minus P dV minus V dP. Again, this is a review, so I'm missing some steps. Okay, I'll tell them, but I don't write them down. So now, if you substitute this du into this equation, what are you going to get? TDS will be equal to DH minus PDV, which will cancel with this plus PDV, okay, minus VDP. So this will give you TDS will be equal to DH minus VDP. And this was, when we did the derivation, the second Tds relation. So, all right. So the two Tds relations we had, Tds equal to du plus PDV, and Tds equal to dH minus VDP. Okay? All right, so let us use the first one. So now let's say for an ideal substance, what does the ideal substance assumption mean? Is that the substance remain within the same state. If it's remain within the same state, what happens? We could use what? The ideal gas relation. If it's a gas, I don't remember if it's R bar or no R bar. But what else can we use? The change in internal energy will be equal to mCV dt, or the dH could be equal to mC sub P dt. Okay, I'm probably going to move anyway to on the derivation, I'm going to move to specific values, might be easier. Okay, so let's start by the first one. So let's say we use this one here, which is what? TDS equal to du plus PDV. I mean, we can use this one, doesn't matter. Okay, so if it is an ideal substance, this should be equal to what? TDS, the change of internal energy will be proportional to what? mCV dt. And if the relation we have PV equal nRT, I don't know if it's R bar or no R bar, okay? This will give us what? P is equal to nRT divided by the volume. So that means here that now I can write this term here plus nRT divided by V times dV. All right, so now what happens if I move the T, I divide both sides by T? You're gonna get ds equal to m CV dt over T plus nR, the T will cancel out, dV over V. And again, this is something we have done. But again, the important thing is that, I mean, it's not a matter of memorizing, okay? So now, if you need to calculate what is the change of entropy, what can you do? You can integrate S1, S2. So this will give you what? S2 minus S1 will be equal to M CV log T2 over T1 plus NR log V2 over V1. And this is basically the change in entropy. Okay, now let's say we use the second one, this expression here. So which is what? TDS equal to DH minus VDP. So again, we do exactly the same thing. This will mean what? TDS will be equal to M, this time C sub P dt, plus, minus, if you solve for V over here, you will have what? nRT divided by P, okay? So minus nRT divided by P, you solve for V from this equation, and you get here dP. You divide both sides by T, you get ds equal to mc sub p dt over t minus nr, the t will cancel out, dp over p. You integrate, and this is the expression we used on the last problem. Oops, sorry, this is, so I did a mistake here. This should not be T1, this should be T1, T2. This should be V1, V2. No, only as for the first one, okay? T1, T2, P1, P2. So you get again here that the change in entropy, S2 minus S1, equal to delta S, equal to M, Cp log T2 over T1, minus nR log P2 over P1. And I think that was the expression that was used on the last problem, that I kind of rederived for the specific problem, because I don't like engineering to be like cooking, that you just need one equation and you go and substitute, okay? All right, so I kind of redid the derivations over here and the understanding, so I hope it's a little bit more clear. All right, so I remember when we did this, probably the first problem that we did in class, generally the one I do, I'm pretty sure the one we did. I don't know the values, but that should not matter. So probably, I think probably the first problem we did will be, let's say that we have a closed system, all right? In here, there is a membrane, and generally the problem we do here is that we have hot water on one side. Let's say T, this is T hot, and you have a certain quantity of water, let's say MH, okay? And here you have cold water and a temperature Tc, and is the center of mass or quantity of water and cold. Okay, so probably the two questions that you had to solve in this problem was find, so let's say now you remove the membrane, what's going to happen? The hot water is going to mix with the cold water, and you're going to get warm water, no? Okay, so I think the first thing was to find the average temperature of the system. And then initially you have hot water and cold water. After you mix it, can you get again hot water and cold water? No. So basically that means that this process is irreversible. So basically it means that the delta S will be different than 0. Correct? Okay. So basically when we did this problem, I don't want you to go and say, okay, first, if I ask you, which one of these two do you have to use? To be okay, I mean, what type of system is this? Closed. So the closed generally is related to what? To the du. So you could get a guess is this one, no? But let's not guess, okay? So if you have this type of problem, what you need to realize is what? Okay, I know the Tds relation, so you don't even need to know the Tds relation the way I started last time, but I want a bit fast to say, okay, what is the first principle of thermodynamics? Q minus work, if I neglect kinetic and potential energy, equal to du, okay? Or I rewrite that one as delta Q minus, if you want to do it now, what will be the work? PDV will be equal to du. So this is the first principle. Then, what do we know about the enthalpy? Sorry, the entropy. The definition of entropy is ds equal to what? Delta Q over T, or you can say over here delta Q is TDS. It's the same thing we just did. So generally, this is the way I will present it. If we combine these two equations, what do we get? The same equation that we had before, TDS equal to du plus PDV. Okay, if you get lost, stop me, okay? But I think this is exactly the same thing. All right, so this takes 3 lines. All right, now in this problem, this is what? This is a closed system, no? So generally, if we deal with closed system, we want to deal with internal energies that are related to the CVs. But if this is a closed system, what do you know about the volume? Volume is constant, meaning that dV will be 0, no? Okay, so you see, you don't need to rederive everything. So you know this is 0. Next, if this is hot water and cold water, I don't know if it depends how hot and how cold it is, but if you make the assumption that the water remains in the same state, liquid, this is liquid hot water, liquid cold water, you're going to get liquid warm water, you can say what? That du is approximately equal to what? M CV dt. Yeah. So from this equation, you can say that ds is equal to m you divide by t CV dt over t. We integrate, I mean, the same thing that we just did. But I'm just trying to show you that it's not a matter of memorizing the equation. It's for each problem, you might have to work it out, no? So this will give us what? That delta S, the change of entropy, S2 minus S1, will be equal to what? M CV log, and let me put over here T final, T initial instead of T1, T2. Okay, so in this case, what does that mean? Because the volume is constant, what happened to this equation? This term here disappeared. Because what would be log of 1 is what? 0, no? Okay, so this term disappeared. But anyway, I'd rather you do this. Okay, it's what? 1, 2, 3, 4, 5, 6 lines. All right, so now you know that the change of entropy is equal to this. But what are the 3 temperatures that we have? So if we look at this problem when we did it, maybe zoom out if I can. I cannot. Okay, so this is this problem. So So initially, let me put over here. So initially, you have hot water at a certain mass, cold water, certain quantity, and at the end, you're gonna get here, let's say T average. So, I mean, we did have to find the average. I'm not gonna be doing this problem. And here you will have, basically will be, whatever, we don't need the math, but it will be M hot plus M cold. And here I put twice M cold, it should be M hot. Okay, so what's important over here? This is initial, final, okay? So the total change of entropy, probably when we did this problem, should be equal to what? Okay, in this case, what's gonna happen? The hot water, what's gonna happen to the hot water? The hot water is probably gonna lose some entropy, no? So we have here M hot CV log of what? T final, which would be the T average. And what will be our initial temperature for the hot water? Will be T hot. Okay? Now, what's going to happen to the cold water? Probably the cold water is going to gain some entropy, no? Okay, some energy. But this will be plus M cold C sub V log of T average over T cold. Okay. So again, I'm not going to go into me. I'm just doing general, but this value should be what? Negative, because the hot water will have more energy, so we'll be losing some of it. And what will happen to the cold water? Probably will be gaining some enthalpy, and that will be positive. And at the end, what should happen to the final result? I mean, in this case, it's just going to be higher than 0, because this term here needs to be, this one needs to be higher than this one, because this should always be positive, no? Given the increasing principle of increasing entropy. Okay, so this is one example we did, and you see here the masses as constant because this is a closed system. The other day, last class, somebody just remind me here, but please, yeah, I think I remember the one of the pipes. So I think it was one pipe, thick pipe over here, and it was here with two pipes, no?
Yeah, right.
And we have this. We had this, we had this. Yeah, now I kind of remember, but not too much. But basically, I think we had. Yeah, now I remember the problem with the mass flows that we have, no? And this was our control volume. And supposedly, I think they say that you had here, whatever, 1, 2, and 3, no? And if I remember right, they were saying that the pressure was basically constant throughout the whole thing, no? Okay. So I don't remember what we had to calculate, but obviously at the end we needed to calculate what was the change of entropy, no? Or what they call the entropy production. So I think I told you that the textbook, I think they always ask you for that here, the variable sigma. And for us, this should be the total, what I call the principle of increasing entropy of the universe, that we have one component should be equal to the entropy that the system might be sharing, gaining or losing with the surrounding, yeah, with the surrounding, plus whatever happens within the system. That generally is, since this system is an open system, what should it be? Should be generally should be M, if you want to look, M delta S, no? But since this one they use mass flows, what should be this one? M dot. Okay, and really this should be for unit S, it should be delta Q dot. Okay. Okay, but in the problem, I think they told us in this system, in the problem that the system was insulated, no? If it's insulated, what does that mean? That Q is equal to 0. So we had this term was equal to 0. So before doing the problem, what do we need to do? We needed to find, okay, what is the change of entropy equal to, no? All right. So I think when I started to do the problem, I think that's where I started losing you. I say, okay, I don't know the expression of this one, but what do we know about this system? This should follow again, the first principle of thermodynamics will be, but this time will be Q dot minus power will be equal to, again, du, but this time will be in function of time. So we can put the dots at the end or at the beginning. Let's put them at the end. Remove the dots, we put them at the end. So this will be the same. And then the other equation, or we use this as delta Qs, would be this. And the other one we know is that the change in entropy is equal to delta Q over T, or delta Q equal TDS. I mean, here it doesn't matter because it's going to be 0. But again, the same thing as before. So from here, concluded that we have TDS minus PDV will be equal to du. All right, or from here, I don't remember what I wrote, but I wrote this probably TDS equal to du plus PDV. Okay, so over here, now let's say that we're going to use the second Tds relation. I'm not going to do the derivation. Let's just show it to you. All right, we're going to use this expression. I mean, let's just do it, okay? Let's do it that way, okay? Let's see what happens. Okay, I'm probably going to get lost like last time, but I want to make sure that we know something. Okay, so if this is, now if we say that the air, this was air, so air is an ideal substance. So I think we say we could use the relation PV equal nRT. And we could say that du is basically equal to mc sub v dt. So that means that we can rewrite this as TDS equal to m cv dt plus, let me rewrite, so we know P here. Okay, so let's rewrite P as what? As equal to N RT over V dV, which is the same thing that we just did. If we divide by T, this gives us ds equal to M CV dt over T plus NR dV over V. All right. So this will give us that after integration, that delta S will be equal to M CV log, let's say T final T initial plus NR log V final V initial. Okay. And if I remember properly in this problem, now let's rewrite this term over here, okay? I think that's what we did last time. So this term over here will be log V final over V initial, let's say. And if we use the ideal gas relation again, what do we get? PV equal nRT. This will mean what? V is equal to nRT divided by P, and this will be nRT. So P final, so nRT final, P final, P initial, T initial. And because the pressures were constant, we ended up saying that this was equivalent to T final over T initial that we knew, no? Okay, so page 129. Again, I'm kind of redoing, but without the values, okay, conceptually. For now, substitute this expression into this one. So we have delta S, let me just rewrite it, will be equal to M CV log T final T initial plus NR log T final over T initial. Okay. So now what I did is that I said, okay, delta S was equal to what? M. So we could factor out the log T final over T initial, and that was equal to M C sub V plus what is N? N is the number of moles. So it's mass divided by molar mass times R okay. So basically at the end, what I say is that delta S, since we are dealing now with an open system, we don't need to deal with masses, but we need to deal with what? Mass flows, no? So I said this will be proportional to this log T final T initial of CV plus R over M, that for us would be, I think, R bar, no? Okay, and now I'm even going to lose you. And now I'm probably going to lose you again. What is this? Yes, it's constant. But by definition, what is that? This is, if you remember, this is the definition of C sub P. So really at the end, you could say that delta S would be equal to M dot C sub P log T final over T initial. Okay, so I'm probably losing you a little bit, but again, I'm just repeating because I hope that by repeating, everything will become a little bit more clear. But now imagine that in order to solve this problem, we're going to use the second form of the Tds relation. Okay, so let's say we put over here, or using the second form of the Tds relation, which will be what? Tds equal to dH minus VdP. So you will see that with some understanding, things can go a lot faster. What do we know about this system? About the problem over here? What do we know about the pressure? The pressure is constant, correct? So what does that mean about dP? Zero, no? Okay, so now we write this as what? Tds. We know that dH will be proportional to what? mCp dt, no? So again, if we do the same thing, you will have ds will be equal to mCp dt over t. We could integrate. And what would that give us? S2 minus S1, which is the change of entropy, will be equal to what? mCp log of T final minus T initial. And if we use mass flow, you will use here a dot. So you see really that I did it using the normal, but if we have used the modified Tds relation, all this problem was 4 lines, no? Just to realize that the Cp is really the Cv plus R over M over here. So I probably guess that this is complicated. This is probably the most complicated material of the class, no? To fully understand it. But I think that by just redoing it multiple times, it will get more clear. It's like repetition is learning, no? Okay, so in general, let me give you a hint. I think I already gave you like 2 or 3 times, but so if you are dealing with a closed system that we say is either this or either this. What is the quantity you're going to be dealing with? You know, if you will basically be dealing almost all the time with internal energy. If you are dealing with internal energy, what do you know? Internal energy is what? Proportional to what? M C sub V dt. Okay, so in that case, all right, if you want, I'm going to redo the very quick derivation. What should be the expression of the first principle of thermodynamics? Would be delta Q minus delta W would be equal to du if we neglect kinetic and potential energy, and you will have that ds equal delta Q over T. So if you combine these 2 equations, I've done it like 4 times already today. What do you get? You're going to get Tds minus partial W equal to du. And I will use this form of the expression, where this is equal to what? PdV, no? So if we are dealing with this one, what will be the value of this term? 0, because the volume will be constant and this will be 0, no? But if we deal with this one, then you will have this value will be what is the work done by the piston, correct? And you will be dealing with this. Again, this is for an ideal substance. So I will use DUs and this, okay? Now, if we are dealing with what I call an open system, but they like to call control volume in the books. So basically, what is the definition of a closed system is that the mass is constant. What is, if you want a definition for an open or control volume system, it's just like the one we just did. They call it control volume because what you control is the volume through which you have a mass flow, okay? And I call it open because it's open, okay? Some people call it control volume because there is mass flowing through the control volume, while in the closed system, the mass is constant within the system, no? Within the volume, the control volume. Okay, so in that case, again, what is safer for this one? Again, if you deal with a closed system, you're going to be dealing with what? It's easier to remember that you need to deal with enthalpies. Okay, and this is enthalpy. It's always safer, okay? And you know that the enthalpy will be proportional to what? MC sub P dt. So now we're going to need one extra step, but basically you have for the same thing, you will say delta Q minus delta W equal to du. And this will be ds equal to delta Q over T. So basically you end up to the same relation here, Tds equal to du minus PdV. But now it's going to come the new thing. If you have an open control volume system, you don't want to be dealing with internal energy. You want to be dealing with the enthalpy. Now, what is the enthalpy? Is U plus PV. So if you take the derivative of this one, you get dH equal to du plus PdV. I mean, we just did it before, plus VdP. If you substitute this expression into this Tds relation, we are left with Tds equal to dH. I mean, it should be the 7 Tds relation. So you see, for here you solve for du will be equal to dH minus PdV. So du will be equal to dH minus PdV minus VdP. What happened here? Oh, when you move this one to the side, this becomes positive. Sorry. This is one is positive. Yeah, I was trying to think. So this becomes positive. This one moves to the other side is positive. Okay. And now what will happen? Du will be equal to what? dH minus PdV. This one will cancel this one. Okay. And this become now minus VdP. And again, here, these are the two forms of the Tds relations. So depending if you are dealing with a closed system and open system, from these two relations, you can derive what would be now the change in entropy, no? Okay. Okay, and that's basically what I use all the time to solve the problems about this. I follow these rules. Okay, so let's finish the problem conceptually. So now we know that the change of entropy, okay, should be of, okay, so let's go to the previous page. This is not what we're looking for. So now from this equation here, we knew that the change of entropy is basically, let's say, should be proportional to this one. Okay, MCPs. All right. Okay. So in this problem over here, let me redo the figure very quick. This is our control volume. This was M1. This was M2. And this is M3. Okay. So over here, the first thing we did is that they say steady state. So we know that there is conservation of mass, meaning that M.1 plus M.2 will be equal to N.3. Okay. Okay. And next, let me go back to this equation. Is what it took me a while to solve the problem, because this is basically what's going to happen. All right. Okay. The equation I scratched over here, but if you want, what happened here is that we are looking at what is the change of the entropy. So that should be what? S final minus S initial. Okay. So what is the final value of the entropy? Should be M3 S final minus, or M3 S3, sorry, if you want. So you want let's see what I use here. I think I use S3 and then S1, S2. Yeah, so you see. So it's so we have M3 S3, to use the same notation we did last time, it would be M3 S3 minus what would be the initial entropy, will be whatever is over here, M1 flow 1 S1 minus M2 S2. Okay. And now what do we know about M3? This is M1 plus M2 S3 minus M.1 S1 minus M.2 S2. So if we rearrange this, we had that the total change of entropy will be equal to what? M.1 S3 minus S1 plus M.2 S3 minus S2. Okay. And what are these over here? The delta S. Okay. And what we just derived? We just derived that the delta S, we have it here, were proportional to what? Basically M dot CP log T final over T initial. Okay. So the total change of entropy here will be equal to what? So this M will be equal, will be M1. If we use this notation, CP log of what? T3 over T1 plus M dot 2 CP log T3 over T2.
What happened to the M1 on the outside?